Namaskar my dear friends. Let us talk about BLDC motor drivers. So what we will do is we will take up low power BLDC motor driver applications, and in this we will try to understand how BLDC motor driver circuit can be designed and how we can make it very useful for our low end application, let's say white goods or fans or blowers or pumps, all these things. So basically one of the IC we will take, which will be DRV10974, and this will be applicable for application up to around 12 volt 1 ampere ratings. So basically a lot of applications are there, which is, let's say, 2 watt 5 watt application, 8 watt application, 12 watt applications. So these small applications, these kind of ICs will be very useful. And the very best thing is this BLDC motor driver will not need lot of codings or something like that. A standalone simple circuit will be enough to drive your motors. Okay. So first, let us try to understand from a typical schematic diagram what are the things we need to set up, right? So let us say we have one IC which is BLDC motor driver. Now what do we need to do on in this particular IC is we need to give one supply voltage which will be, let us say, 4.4 volt to 18 volt rating it has given. So you can give it, let us say, 9 volt or maybe 12 volt. So 12 volt I am preferring because it is very generally available. So 12 volt will be giving at the supply voltage. Okay. Next comes up is a charge pump circuit. So charge pump circuit we will be needing, let us say, 1 microfarad capacitor. Then we will require some of the different resistors to set some of the things like lead angle. So lead angle can be set by one of the resistor. I will tell you what is lead angle and how it can be set for different angles. Then we have acceleration profile, that is nothing but your ramp rate of the motor, like how fast you want to start it or how slow you want to start it. So that is nothing called as ramp profile or acceleration profile. Now coming back to the FG pin. FG pin is nothing but your like speed feedback coming from the out IC. So this IC is there which is going to give you what is the speed that at which the motor is running, right? So this can be taken to some of your like I2C line or something like that. So this will be acting as a data line, so you can connect it to a SDA line or simply you can pull it up and keep it like not connected to anywhere. That will also do. Next very important thing comes up is FR pin, that is nothing but it is a direction setting pin. So you have a motor which is having U, V and W phases. So whether you want it in U, V, W or U, W, V, okay. So which way you want to rotate it, either you want it to rotate in forward direction or reverse direction. So this can be set by one of the pin, which can be set it by like a pull up or pull down, or maybe it can be controlled through a microcontroller GPIO as well. So we will give you two application, one will be a standalone application and another one will be like with microcontroller application, both. The very important thing that comes up is PWM. Okay, so PWM actually is the factor which is going to set the like drive voltage at the motor, and this is how it will be setting the speed of the motor running, right? So either you can give one PWM signal at this particular pin, or otherwise you can give one analog voltage also, which will be like 1.8 volt maximum or less than that will be setting the output speed. There is one more thing that is need to be set is current limit. So current limit, let us say this IC is having the capability of up to around 1 ampere rating or maximum 1.5 ampere also it can go for peak pulses. However, I would like to run this motor, maximum current output is, let us say, 0.5 ampere. So for 0.5 ampere there is a current limit resistor setting that we can set it so that the current coming in UVW phases will be less than or equal to this particular set value. So as you can see very easily that only these many components are needed to make a BLDC driver circuit so that you can run your motor very easily. So before proceeding to that, we can see, since I am working on lot of like Texas Instruments motor drivers, so I'll just give you a brief idea about what are the products that is available. So as you can see, based on the like power rating, we have up to 12 volt 12 watt, then we have 40 watts, then we have 80 watts, and we have 80 watt to 1 kilowatt. Okay, And the design that is available with our uh, training and sessions is DRV 10964, we have DRV 10974, which we are going to discuss today. Okay, and then we have even little bit higher power rating, so that is called MCT 8315 and MCT 8316. So these three ICs are very versatile and very important. If you want, you can go ahead with MCT 8315C-Q1, which will be for automotive application. Okay, and you can see there is very nicely set this particular table, which is like censored trapezoidal, then we have sensorless FOC, then we have sensorless sinusoidal, and we have sensorless trapezoidal. Okay, so we have developed application for sensorless sinusoidal, so that you don't have to work with censored signals or something like that. Okay, so why don't we go ahead and directly get into the design and techniques of this particular BLDC driver, which we have in our mind right now, which is going to be DRV 10974. Okay, so DRV 10974 is a BLDC motor driver. It can be utilized for your application, which can be fan, blower, pump, or BLDC motor driver modules. Okay, and this can give you up to around your 12 volt applications for 3-phase sensorless BLDC driver motor driver. Okay, and this is having a very good package, which is HTSSOP 16 pin package. One more package is there, which is little bit like QFN package kind of thing. So QFN package I am not using because it has inside pins. Okay, however, that is also same. Coming back to the features of this particular BLDC driver, so it can take voltage range up to 4.4 volt to 18 volt. It has total driver H plus L like RDS on is 750 milliohms. Okay, less than 1 ohm it is there. That is like high side driver and low side driver of MOSFETs. Then we have phase drive current continuously, it can give you up to 1 ampere of current, and peak current it can go as high as 1.5 amperes. Now if you see, we have 180-degree sinusoidal commutation for optimal acoustic performances, and the best part is, just now I have already explained you, for lead angle you have resistor to configure lead angles. Same way resistor configurable current limit also is there, and resistor configurable acceleration profile is there. So this is used for your soft start like applications. It has built-in current sense to eliminate external current sense resistors, so you don't have to put external current sense resistors. So how much current is there in the motor driver. Now the best part is it has proprietary sensorless control without motor center tap. Okay, so you don't have to require a censored signals, and simple user interface, 1 pin configuration for soft start, PWM input for designates magnitude of voltage applied to the motor. Nothing but I told you, right, like PWM duty cycle will be utilized to set the voltage level at the output side, so that you can have higher speed or lower speed based on the duty cycle of PWM signal, right. This can be also set by a simple analog voltage. Now we have open drain like FG output pin, which is going to provide you a speed feedback, and then pin for forward and reverse control also. It means the motor can be directed into forward direction or reverse direction. This we have already discussed. It is fully protected from your motor lock, detect and restart. So if you motor locked because of some errors or something like that, it is protected. It has a protection of overcurrent, short circuit and over temperature, as well as under voltage lockout, right. So under voltage lockout is also there. So we have already seen the typical schematic that was there, and now we will try to design this particular circuit based on the requirement. So before that, what we will do is we'll try to understand what are the things that can be done to do all these jobs, like lead angle, acceleration profile and voltage supply, all these parameters. Okay, so after doing these particular design cycles, we will be able to land up into this particular a standalone design implementation. So this is the complete circuit that I have designed it, and this is the power supply. We will explain you later, and this is the values of each and every parameters, like what is the ramp signal and what is the like current sense limit and all these things. So this will be understandable much better once we go through the design steps. Okay. So before landing up on this page, what we'll do is we'll try to get into the design steps. All right. So as you know already, this is the pin configuration that we talked about. So this is a 16 pin IC. Similar to that, we have another QFN package which is going to be 16 pin IC with thermal pad both. Both of them are having thermal pad for heat dissipation. If you talk about pin configuration, so this is my ADV pin, that is nothing but your acceleration profile, sorry, it is for lead angle pin. Okay, so lead angle will be set by 1/8 watt of resistors. Okay, then we have CS pin, that is your current sense pin. So current limit, how much you want to set, that you can set it through the this particular CS pin. We have FG pin, which is going to give you the feedback, speed feedback. Then we have FR pin, that is nothing but it is going to set your like direction of the motor driver. So there is nothing but it is if it is 0, then it will be UVW, and if it is 1, then it will be UWV. Okay, so this is how the motor direction control will be done. Then we have ground pin. So ground pin can be directly connected to the your analog ground. We have not connected pin as well. Then we have PGND pin, that is your power ground pin. So right now for very simple application, I am going to put this ground pin and PG ground pin both same, so that no need to make the design very complex. We have PWM pin, which is going to like control the motor speed. So motor speed will be controlled by this particular PWM duty cycle, or otherwise it can be also given some analog voltage, right? Then we have RMP pin, that is nothing but your acceleration profile pin. So how speedily or how slow you want to start the motor. So this is how it will be set by this acceleration ramp control input. Then we have motor phases like U, V and W is there. So you can see U, V, W, these are the three motor phases that we always needed. And we have one LDO regulator for your internal operation, which is 1.8 volt or like 1.8 volt regulator, and it must not be loaded externally more than 3 milliamperes. So we will be just using it for a standalone purpose, so that we can do not load this. And at the same time we have VCC pin, which is going to be power supply connection. You needed minimum 10 microfarad capacitor at this, but we will be using a little bit higher. And at the same time we have charge pump, which will be requiring 100 nanofarad of capacitance. Okay, so this is the complete pin description about this particular IC. Now coming back to the electrical characteristics. So let us say supply voltage. Supply voltage must be between 4.4 volt to 18 volts. So our application will be 12 volt. Okay, then we have other voltage ratings for each and every pins. So you can see motor phase pins can go up to 18 volt. Then you have PWM and FR pin can go up to 5.5 volt. That is nothing but your PWM logic labels as well as your direction setting pins, right? Then we have FG pin, that is nothing but feedback speed pin. So this feedback speed pin will be taking up to 18 volt input. Okay, so directly it can be pulled out through the voltage supply as well. There is no problem with that. We have current setting pin or current limit pin, so that is going up to 1.8 volt maximum. So you must not give more than 1.8 volt at this particular pin. And we have PGND ground pin, and then we have ramp and advanced ADV pin, that is your lead angle pin. So ramp is your acceleration profile pin. So this can also take up to 1.8 volt max. Alright, so with this you can just see what is my ambient temperature working. So that is up to 185 degree centigrade, and junction temperature can go as high as 125 degree centigrade. You can see we have junction to ambient thermal resistance as well. So for HTSSOP package it is 37.8 degree centigrade per watt, and for VQFN package it is little better, which is going to be 34.5 degree centigrade. So the best part is both of them are having same thermal capabilities almost, so there is no need to worry about this. Alright, so we have understood the recommended operating conditions. Now we'll talk about block diagram of this particular IC. So why we are talking about block diagram is actually it helps you to understand, if you are a beginner, it helps you to understand what are the things that is there inside the IC and how it is controlling all the functionalities. So as you can see, we have high side and low side drivers for the three phase. We have U phase, V phase and W phase. So all these three phase we have high side and low side driver MOSFETs that is going to give you the motor driver output, right? And it has pre-driver inbuilt ICs as well, like phase U, phase V and phase W. Coming back to the input side, we have like 1.8 volt regulator for your input purpose, like in internal regulator purpose. Then we have PWM control. As you can see, we have PWM control here. Then we have FR pin, that is your direction setting pin, whether it can go low or high. If it is not connected, you can see it is pulled low, so it means it will be working for low direction. So you can see here for low direction it was forward direction UVW, and for one it is UV, UWV. So if you want, you can leave it open also, so that it can work with low. So for making it very definite, what do we do always is we can always pull it down permanently. Then we have acceleration profile pin, which is having one ADC inbuilt inside. Then we have current setting pin or current limit pin, and then we have lead angle setting pin. So these three resistors will be needed to set all these three profiles. Now coming back to the ground and power ground, so both of them can be sorted together, there is no need to worry about this. And coming back to other part, we have charge pump capacitor, that is also called as bootstrap capacitor. So this capacitor will be put between VCP and VCC, and VCC will be accompanied with one more capacitor which will be acting as a bulk capacitor or a storage capacitor. So this is all about this particular thing. As you can see, for motor feedback, speed feedback, we have FG pin, so that is pulled up internally. If you want, you can leave it open, or otherwise you can pull it from outside as well. Otherwise you can send it to your PA of your I2C signal, so that it can give you the what is the speed of the motor that which it is running. So you must connect it to something, so that it will be giving you what is the speed that is working. Let us get into more deeper about this particular motor drivers, like how it works and what are the things that we need to take care of. So as you can see, we have speed input controls. So speed input controls is nothing but, let us say we have UV phase, VW phase and WU phase. So as you can see, they are phased with little bit differences, right? So you can see the black lines or the black dark line is having PWM input, and this is the average value that is calculated. So PWM input, as my duty cycle is increasing, duty cycle is increasing means, let us say this is my PWM signal. So this is the time on and this is the time off, okay? This is time off, this is time on. So my duty cycle is nothing but time on by total time, that is nothing but T on plus T off, okay? So if you want to reduce the PWM duty cycle, you have to reduce the T on, so it will be reduced like this, understood? If you want to increase the duty cycle, then my high signal will be reduced and low will be reduced. So this will be high. So this is having higher lower duty cycle, and this is having higher duty cycle, understood? Now coming back to the output voltage that you will be seeing at the motor. So you have U, V, W phase of the motor. So what is the voltage that you will see? So let us say VCC is the supply voltage, which is 12 volt. So if you are going to give PWM 50%, so 50% means you will see 6 volt at the output of the motor, okay? This is the understanding that we should have. So the motor speed and control will be basically tested by this PWM signal, which will be going up to 100% as well. So if you put it 100%, my VM will be equal to your VCC supply that is there. If it is 50%, then it can go up to half of the supplied voltage. So what is happening is, PWM command input control, how it works? Basically you are giving PWM input, then it is passing through a low pass filter, then it is going to go ahead with amplitude of output sine wave, and then it is going to go to PWM output, okay? So as you can see, first one, it is giving you almost 100% PWM input, and it is reaching the voltage level at VM level, okay? then for half or 50% PWM signal, it is going up to PWM by 2. So you can understand it much more easily, like motor speed transfer function is nothing but your voltage output that will be seen, which is VPH PK, right? So VPH PK is nothing but depending on your PWM label. So PWM label, based on that it will be giving you the output, right? So what is happening? You must have the PWM between 15% to 100%. Less than 15% is not recommended at all. Okay. So this is using PWM mode control. What is the voltage at the UVW phase of the motor? Now there is one more mode which I was talking to you about all the time, which is analog mode. So what you can do is you can put analog signal, which is VANA. So VANA will be deciding what is the voltage at the UVW phase of the motor. So if you put it 1.8 volt, so 1.8 volt is down, you can see, so it will be giving you 100%, and if it is lesser than that, then accordingly the voltage output at UVW phase will be scaled. Okay. So you must make sure that the voltage level is more than 0.27 volt and less than 1.5 volt. Okay, so 0.27 volt to 1.5 volt is recommended range, and similar to that for this particular PWM mode you have to have 15% to 100% range. Okay. Good. So we have understood how to control this speed. Now as I was talking to you about the motor direction change, so motor direction change, if you keep FR pin to be 0, it will be UVW phase, that is your forward direction. And if it is FR pin is 1, then it will be reverse direction. Understood? So this is how we will be working up. Coming back to this motor frequency feedback pin, so motor frequency feedback pin, you will be seeing a frequencies of signal which can be decided by this. So that will be ramp rate, which will be RMP is equal to F of Fg into 60 by pole pairs. So that is going to give you like some of the like frequencies that will be coming as a feedback speed. Okay. Anyway, we are going to see some of the lock detection, because this particular IC has the capability to detect lock conditions and act accordingly, or otherwise it can the motor can get destroyed. So to protect that, we have lock detection mechanism, right? So lock detection can be happening in this particular scenarios, like we have KT measures, we have no motor connected, then also it can tell you that okay, motor is locked output. Then we have output loop abnormal or open loop abnormal, we have back EMF abnormal, then we have closed loop abnormal, we have a speed abnormal. So any of these particular scenario occurs, okay, then it will go through the OR gates, and this OR gate is going to give you the high impedance, and this high impedance will make sure that motor output is locked, like you will not be getting any output at the UVW phase. Okay. So this is how it is going to detect the lock conditions and act to protect the motor and the device that is connected to the output. Alright. So this was all about lock detection. Coming back to current limit setting. Okay, so current limit setting, this table is going to give you an understanding like how much current you want at the UVW phase of the like motor output. So to drive the motor, we need some maximum current that is needed. So based on this particular setting of RCS resistors, you will be able to set the current limit that you want. So basically I have designed lot of application up to 800 milliamperes, so you can connect a 38.3 kilo ohm resistor at the RCS pin. Okay. Based on your need, let's say you need very less current, then you can go ahead with 400 milliamperes also, and even 200 milliamperes also. Okay. Now as I was talking to you about acceleration setting, or that is nothing but your ramp setting. Okay, so ramp rate setting will be done by again one more resistor, which will be called as a RMP. Okay, so this RRMP will be acting to give you ramp selection of codings like 0 to 15. Alright. So what will be the acceleration rate? So you can see acceleration rate 2, acceleration rate 1 in hertz per second, and per second square is there. So this is nothing but per second square, and this is nothing but per second. Okay. So generally like you can start with very lowest value and then later on you can increase this to higher value. So we'll be starting with 7.32 kilo ohm like ramp resistor settings, and then after setting the lead angle we will be able to set this particular value to highest value. Okay, so that is called as motor tuning. So motor tuning we will understand how to do that. So coming back to lead selection, as I was talking to you, so lead selection resistor will be utilized RADV. So RADV lead time how much you want, so it can give you 10 microsecond to 1000 microsecond, that is 1 millisecond. Okay, so with this you will be able to set your like lead selection. So I have generally utilized 400 microsecond always, okay, because it is like optimal for my designs. So 59 kilo ohm you can utilize. And so once you have set the lead angle or lead timing, then you can go ahead with your acceleration setting to higher value, so that your motor start will be normal and speed. Let's come back to typical application. So we have already talked to you, so you can see we have ramp rate setting was 59 kilo ohm, then we have forward reverse direction pin, we have feedback like a speed control pin, our feedback, what is the speed feedback that will be done here. Then we have PWM input pin to keep the like motor speed in control. We have a regulator pin which is V1.8 volt. Then we have ramp rate setting or nothing but acceleration setting, so that is there. Sorry, this was your lead angle setting. Okay, so lead angle setting was 59 kilo ohm. Then we have ramp rate setting, that is your acceleration profile. Then we have current limit setting, which is 115 kilo ohm. So based on the values of each one of the resistor, we can see what is the current limit set. So current limit set will be actually 115 means 1400 milliamperes maximum. Okay, so that is not recommended actually from beginning itself. Acceleration profile setting was how much, 7.32 kilo ohm you can see, which is the lowest one, and 59 kilo ohm is your lead angle setting. So lead angle setting is 59 kilo ohm, is nothing but 400 microsecond. Okay, that's all. We have charge capacitor, charge pump capacitor, then we have like supply voltage, which is going to be VCC, that is nothing but your 12 volt. And this is your motor connection, which is going to be your U, V and W phase, and this is your power ground and ground, so both will be same, right? That's all. So these things we have already done. So I mean in this particular like application, I had already told you like what is the like lead angle selection, so that is 400 microsecond, that is current limit 1400 milliampere, and then it is ramp rate settings, that is acceleration profile, which is 0 code is used. And if you want, you can give a PWM input through some of the like potentiometer or maybe variable resistors, or otherwise you can give a PWM input also. And then this will actually go to like your SDA pin. Okay, and then this particular like a direction setting will be done by either pull up, pull down, or you can set it through one GPIOs. Alright, and this is the motor connector that you can connect it through a connector, and you can like add additional 0.1 microfarad capacitor. Okay, so let us now proceed to the design that we have implemented. So as you can see, this is very simple design. I have kept pin configuration as it is, like 1 to 8 and 9 to 16. Alright, then we have set the like lead angle and ramp rate and current setting. Based on this particular three things I have written here. So acceleration ramp rate code is selected 8, so that's the reason I have put it 49.9 kilo ohm. Then we have lead angle selection, which is 400 microsecond, that is 59 kilo ohm, and we have soft current limit, which is 800 milliampere, that is 38.3 kilo ohm. Okay, so after starting with 7.32 kilo ohm, you can like once lead angle is set, then you can start increasing this particular ramp rate resistor to make it at the highest speed startup, right? So that's the one thing that you can do. Another thing we have done is we have direction setting resistor. So by default I have kept it low so that it can start with U, V and W phase direction, that is forward direction. And we have FG pin that I have put it pull up so that you don't need to send it to outside. So this will be your standalone application. Okay. If you want, you can start with this PWM input. So PWM input, what I have done is I have given a provision of PWM. However, I have set it through a pot or like a resistor that is 25 kilo ohms. So this will make sure that it is going to give you a required amount of analog voltage at this particular setting. Let us say if you want to reduce the cost, so once it is set, like once you have set the analog voltage requirement, based on that these two resistor voltage divider you can set it and fix the values, and you can remove this particular potentiometer. Okay, so this is how you can reduce a huge amount of like cost. Coming back to the output side, we have charge pump capacitor which is 0.1 microfarad. Then we have VCC. So I have put 22 microfarad instead of 10 microfarad, and then 0.1 microfarad filter capacitor. Okay. And this is the motor control, like a motor connection. So motor connection, you can see U, V, W phase are connected at this particular point, U, V, W. And one more jumpers I have given, so that if you want you can have a connector as like terminal blocks, or otherwise jumpers directly connected to ribbon cables kind of thing. Okay. Coming back to the power supply, so I have given two provision. One is like the simply connector is there which will be taking up 12 volt power supply input. If you want you can give it even a little bit higher volt, but however I have protected it through a Zener diode here. Okay, or like TVS diode it is. Then we have given bulk capacitor which is 100 microfarad electrolytic and 0.1 microfarad ceramic capacitor. If you want to power up this board, you have one more provision which is going to be jack, that is your adapter jack, that will be giving you the input. To make it much better circuit, you can utilize one diode here of let's say 2 ampere rating, of let's say 100 volt or 60 volt rating. So this one diode you will be able to utilize so that it can work. Okay. Coming back to one more design, what we did is with microcontroller section. So this was a standalone design, very simple design. If you want to reduce the cost and just keep it in your like your fish pot motor drivers, or maybe any toys, or any like blowers or fan or all those things, this is very easy to work. However, if you want to control the motor speed or something like that through microcontroller, then we can utilize this one. So what I have done is a very simple microcontroller I have taken, which is MSP M0L1105, and this is having like SDA and SCL pin which is going to be utilized for your I2C application, and I2C application has been pulled up here, and then this will be working with your PWM clock and as well as FG pin. Okay, that is your speed feedback pin. As I have already explained several times that this particular microcontroller will be powered by like a VDD, that is 3.3 volt, and then we have like a reset pin, then we have programming connector here, and we have one more connector I have put. If you want to put it like on the same board, then you don't need this connector, otherwise you need this connector so that you can send it to your motor driver PCB. What I have done is, you have the power supply. So this power supply is, let us say 12 volt, then it can go through fuse, it is 12 volt, and now I have put a 5 volt regulator. So this 5 volt regulator will be changing it to 5 volt output. Okay, and this 5 volt is going to get changed to 3.3 volt, that is your VDD. So this 3.3 volt will be actually utilized to power supply this particular microcontroller, and at the same time other pins are connected. Now if you see the motor driver section, so that was microcontroller section. Motor driver section, if you don't need this particular connector, you can put this particular IC section in the same page, or like on the same PCB. Otherwise, if you have a separate router PCB, then you can utilize this particular connector so that you can have a interfacing, right? Now in this particular interfacing, you can see like my ramp rate or current limit and all those things are set already. Now we have direction setting that will be actually due to by microcontroller, as well as I have given a provision for using this one. So permanently it is pulled down, so it is in UVW phase, UVW direction. If you want to change it, you can change it through the IO pin, that is nothing but your PF4 pin. So PF4 pin will be coming as input and changing it FR direction to like a reverse or forward direction. So that's all guys. Hope you have a very good idea about how to design this BLDC motor driver application. And if you want to like work out differently, or maybe you want to select a different motor driver for your different applications, you can put down your queries in the comment box and we shall be able to give you answers as soon as possible for your any applications that is needed. Thank you so much.